Hello, right, we are carrying on now with our section on impulse and momentum, chapter 6, and we're looking at the A-level content, so the remainder of this chapter. So a quick recap at the very start of what we've covered already in the AS content. Just a reminder, we focus on two main concepts, impulse and momentum, and we defined impulse as being force times the time, and we said that the units, if I can get my pen to work, were denoted by Newton seconds, and impulse itself was denoted by the capital letter J. It's a vector, so we make sure we underline that. We also said that momentum was mass times velocity, so simply we wrote that as mv. And we also said that the impulse was the final momentum minus the initial momentum, and we were looking at collisions particularly with that, and so that was defined as mv minus mu. Just a reminder, we always use final velocity as v and initial velocity as u. We also said that the law of conservation of momentum, so that the momentum before a collision is the same as the momentum after a collision. And then we went on to look at Newton's law of impact. So when we had, say, for example, a ball being dropped onto a surface, so we had a velocity or the speed as it approached the surface, and then we also had the rebound afterwards, so the separation, so speed of approach, speed of separation, and we said that the speed of separation divided by the speed of approach was a constant, and that constant was denoted by E, not the 2.71 E this time, but E is the coefficient of restitution. So you should be able to look back in your notes at all of that. If you want to have a little bit of a recap, make sure that you do. This is just a quick review. We also said that if E was equal to 0, then that was a completely inelastic collision. So there's no bounce at all. So imagine if you had something that hit a surface and just stayed there. If the opposite end of the spectrum, E was equal to 1, it would be an elastic collision, fully elastic, so that would mean that no energy would be lost. Now in reality, a ball, for example, hitting a surface would be somewhere in the middle. There'd be some energy lost through diffusive forces, or diffusive energy, sorry, so, you know, sound, perhaps a bit of heat, that kind of thing. But there would be some bounce back as well. And the value of E will tell you how elastic, how much bounce there is. So that's just the recap. To move on now, just a little bit of notes before we start going into some examples. And these are just some definitions really, so you can see how it works and how we can still apply the same processes to either a constant force or a variable force. So we have already said that for a constant force, the impulse is force times time, which we just write as Ft. And let's have a look at a variable force. So for a variable force, we would say the impulse over time is the integral of F with respect to time. Now, when we change velocity from our initial velocity u to our final velocity v, we can integrate that over that period of time. And you can feel free to do this. You'd end up with Ft, substitute in your t, substitute in your 0. You end up with Ft, which is, as we know, mv minus mu. So it's exactly the same. So it's the same even if the force varies. And just to illustrate another point as well, imagine you've got two snooker balls that collide. They're both in contact for a really short time, but the force is not constant during that time. It's 0 as they touch, builds up to a maximum, and goes back down to 0 again when they rebound. Now, if we think about Newton's third law from previous chapters, the force of A and B, we know from the third law is that they're equal and opposite. So all the time, the force of A on B is equal to the force of B on A. They're equal and opposite. So if we think about that in terms of impulse, the impulse of A is the integral of f dt. So the impulse on B, equal and opposite, will be the integral of minus f dt, which is just minus integral of f dt. So total impulse, if we summed the impulses from those two, total impulse would be 0, because they're equal and opposite. So the momentum change as well, also equal to 0. So therefore, what does that say about the principle of conservation of momentum? We know that it applies even when the force varies. Okay, so that's just a bit of background notes. If we turn over then, and we'll have a look now at when we've got impulse and momentum in more than one direction. So essentially what this means is that the forces are at an angle. They're not just in straight lines. So we know that impulse and momentum are both vectors, and the impulse of the force is in its direction, and the momentum is also in the direction of the velocity. So we can represent this on a vector diagram. So essential equipment at the ready, pencil and ruler. So if we represented this in terms of a vector diagram, if we had our initial momentum, so let's pop that down there, that's mu, and we know that we have our impulse. So let me just label these. So we've got mu, I'm underlining because it's a vector, and impulse is j. Then my resultant here, I know this resultant here, so that resultant would be mu plus j. Now if we go back to my, well, it's not mine, but the equation where we said that mv minus mu equals j, so that's the definition of impulse, we can see here that if we added mu to both sides, we'd end up with mv equals j plus mu, and so that is their equal to mv. So we just represented that in a vector diagram, and if we just put that in symbols, I've already done it really here, so we would just say that mv is equal to mu plus j. Don't forget to put your little vectors underneath. And if we wanted to find impulse then, so if we wanted to find j, we could use j is equal to mv minus mu, and we're going to use that in an example a little bit later. So let's have a look where it's in more than one direction. So imagine you've got a ball here, it's hit in this direction by a bat. Its initial velocity was coming along here, it was hit by a bat, so it ends up going in this direction. This just shows the direction, the velocity. This here shows the impulse of the bat with the initial momentum and the final momentum. So again, if we represent those then with our vector diagrams, first of all I'm just going to label these with our notation. So that would be j, this would be our mu, and this would be our mv. And if we then draw that on a diagram, I'm going to use vaguely these directions here, we can see that I've got j coming down there, I've got mv coming here, and now just be really careful with this one. So let's just label these and we'll have a look at that in a second. So here we've got our final momentum. Here we have our impulse. Now remember, impulse is mv minus mu. So when we come to this one, you can see for our picture here, our initial momentum is coming in this direction, but here it makes sense, according to our equation, that it's the opposite direction, it's minus mu. So it's just representing that on a vector diagram. Okay, so that's our first set of notes. Let's have a look at an example then, how we would actually apply this. So we've got a game of snooker with a white cue ball. So that's if you're not sure how snooker works, you have a big cue. So imagine like it's a bigger stick than a pencil. You have a white ball, you hit the white ball with your cue, and then you use that white ball to hit another coloured ball, trying to get it into a pocket. So you're basically creating lots of collisions, which is why mathematicians like to use snooker as examples for this, because it works quite well. But if you're not sure, if you've not seen it before, have a quick Google and you'll get to grips with it quickly. So we've got a white cue ball, got its mass there, and it hits a stationary red ball at 0.8 meters per second. After the collision, the cue ball is moving at 0.6 meters per second, and this is where it changes from previous examples. It's been deflected through 30 degrees, and we've got to find the impulse on the cue ball and show this on a vector diagram. So we start off by looking at, right, what's our initial situation? So like we do with normal momentum, we do our before and we do our after. Now these are going to be slightly different just because we have got the direction and the angles to take care of as well. So our before situation, I'm just going to focus on the white cue ball. So there's my white cue ball, just change pencil for some reason. Let me go back to my initial pencil. Right, so we know that U is equal to 0.8, because it tells me that in the question. It's going in this direction. This is the white ball. You can label that as the white ball if you want to. I'm not going to bother showing the red ball at the moment because we're just focused on the white ball. Now, after the collision, I need to show the direction that this ball is going in. So imagine this was my initial one here. And it's now a velocity of 0.6 at an angle of 30 degrees. So we've got our before and after scenario. So my first step is to write the velocities in terms of I and j vectors. So let's just write that note for myself. Write velocities. Okay, so my initial velocity u, straight horizontal line, absolutely fine. So u is 0.8I. V, final velocity. So if we go back to this diagram here, and this is just about resolving, remember? So you're just resolving vectors. So it's in this direction and we want our horizontal component. So remember our horizontal component will be 0.6 for the velocity, and it will be cos 30I, and then my vertical component will be sine 30j. So again, if you can't remember that, look back at your notes, remember the horizontal component and vertical component. So if we have a look then at what that means for j, we know from before that j is equal to mv minus mu. So I just plug that in essentially. I'm going to do it up here. So just see, I'm shift that up a little bit. So we've got m, which is 0.2 from the question, times v, so 0.6 cos 30I plus 0.6 sine 30j, and then we're subtracting mu. So again, m is 0.2 and u is 0.8I. Now I'm just going to do all this quickly. If you want to pause the video and work all this out for yourself, that's absolutely fine. But I'm just going to speed up a little bit and tell you that it's minus 0.056I plus 0.06j. Again, like I say, have a look if you want to for yourself, if you want to figure that out. Right, so underline that as my nice little neat start point. So I've got the impulse in terms of I and j, but the question is saying show it on a vector diagram back here. So I'm going to scoot this up and we're going to work out now the magnitude and direction. So first of all, to do that, I'm going to draw my little diagram that's going to help us work out the magnitude and direction. Again, you've done all these skills before. I'm just going to pop it over here actually, I think. So it was minus 0.056 in the I direction and 0.06 in the j direction. So let's label that. That's my little right angle. That's my 0.056. It's going in that direction. This is my 0.06. And I'm going to call that angle alpha. So I've got my little diagram to work out the magnitude and the direction. So my magnitude is the length of that hypotenuse. So it's just applying Pythagoras. In fact, I can turn that into a nice equals. So I'm going to have 0.056 squared plus 0.06 squared. Again, you can work that out if you want to, but it comes to 0.0821. And then in terms of the direction, let's work out the angle. So we can work out tan of that angle. So I know that tan alpha is 0.06 over 0.056. And then that gives me alpha is 47 degrees. So again, if you want to work that out yourself, pause the video and just double check on your calculator. That doesn't give me the full direction though, that just tells me this angle. In terms of the direction, the initial direction, if we go back to this diagram, U was going in this direction. So I want to know what that angle is there. So I'm going to call that theta. So I'm going to say then that theta, we know, makes a straight line. So it's going to be 180 minus 47, which is 133 degrees. So therefore, we can say that's an angle of 133 degrees to the initial motion of the ball. So it just shows you how much it's changed from its original path. And then the final part said to find this on a vector diagram, or show this on a vector diagram. So we know that we had our initial velocity. Now remember, we need to remember that J is equal to mv minus mu. So our minus mu, we know u is going towards the right as a horizontal line. This will go towards the left. So that will be our minus mu. We know that our initial velocity was, our final velocity, not initial, our final velocity went at 30 degrees. Just going to draw a little dotted line there just to show the horizontal. So our final velocity, mv, that's 30, and we also know that our impulse, final impulse, was 133 degrees from the horizontal. So I know that this whole angle there to the horizontal is 133 degrees, and that is my impulse. Now, one of the further questions that you can see in the book, it says what happens to the red ball. Now the red ball was stationary at the start, so we can then say that the impulse we know will be equal and opposite to this, so it would then be 47 degrees in the opposite direction. So if you wanted to add that into your notes, you can do. Right, let's move on to example 2. So we've got here a hockey ball of mass 0.15 kilograms. It's moving at 4 meters per second, parallel to the side of a pitch. It's struck by a blow from a hockey stick. It exerts an impulse of 4 Newton seconds at an angle of 120 degrees to its direction of motion, and we've got to find the final velocity of the ball. So we start off exactly the same as we did before, where we do it before and after. And our before scenario, we've got our hockey ball moving in this direction, and u is equal to 4 meters per second. Now in the middle, we draw the impulse and we say what's happened with it. So we know then that we've got an impulse 120 degrees. So we start here, 120 degrees will be around here, something like that. So that's my impulse. I know it's 4 Newton seconds. This is 120 degrees, so I know that that bit there is 60 degrees. And then afterwards, we've got the velocity going somewhere up here. Let's draw a horizontal in, and we'll call this phi. Let's use another Greek letter. Right, okay, so again, start similarly in that we do the unit vectors, so of u and v. So u is 4i, so it's just going in the horizontal, and j is, again, let's resolve, this one here, let's resolve it. So we've got j in this direction, so our horizontal component towards the left, so it's minus 4 and then cos 60 I plus, it's going up, so 4 sine 60 j. And then we're just going to use, so I'm going to put this down so I've got a little bit more space. We're going to use our j equals mv minus mu again. But we actually want to find the velocity, so I'm going to rearrange this and say that mv is equal to j plus mu, substituting what I know. So I know that m is 0.15 from the question, v is what I'm trying to find, j is minus 4 cos 60i plus 4 sine 60j, and I'm adding on mu, which is plus 4i. Now again, pause if you want to work that out, but I'll just quickly skip some stages and say that that one works out to be 1.4i plus 3.46j. Divide through by your 0.15, so your velocity is minus 9.33i plus 23.1j. So I've got my velocity here, but again, we don't want it in terms of I and j vectors necessarily. So draw our little diagram again. So let's label this. So we had, in fact, we can keep that going there. That was our phi. Let's call that one alpha. So we had 9.33 in that direction. We had 23.1 going up. So we can use that now to find the magnitude and the direction of the velocity. So let's find the magnitude. So again, I haven't put my vector under there because it's the magnitude I'm trying to find. So 9.33 squared plus 23.1 squared. Remember, because you're squaring it, I don't need to bother about the negative in there. That works out as 24.9 meters per second. Again, you can work that out on your calculator yourself if you want to. And then the direction. So I can use this diagram here to find alpha and then in turn find my phi. So tan alpha is opposite, which is 23.1 over 9.33, which is 68 degrees. So therefore my phi is 180 minus 68, which is 112 degrees. So therefore I can say the ball has velocity of 24.9 meters per second at an angle of 112 degrees to the original direction of motion.